Hello everyone, my name is Mohanad Al-Murish, and today I'm going to give you a short presentation about my PhD project, which has the title of Engineered Quantum Dot Structures in Glass for Solar Energy Harvesting to Heat Water. It is known that from all the available water in planet Earth, only 1% is classified as fresh water, and this is causing a global water scarcity where it's expected that two-thirds of the world population could be water stressed by 2025. And with the inevitable increase in world population as we are expected to reach 8.1 billion by 2025, this adds more to the global water crisis. According to the World Bank, almost half of the world's population are located in between and around the tropics of Cancer and Capricorn, and these are considered as the worst sufferers in terms of access to hygienic water. Unfortunately, as a result of the consumption of contaminated water, it's estimated that around 3.4 million, mainly women and children, die annually in developing countries. One main problem of current water treatment technologies is that they are energy intensive, where for example 3 to 10 kilowatt hour per meter cube is used in the process of desalination using reverse osmosis. And this amount of energy adds to the global carbon dioxide footprint, but most importantly, such energy intensive processes are unaffordable by the poor nations. That's why, under the United Nations Sustainable Development Goals, goal number 6 is revolving around ensuring access to clean water and sanitation, and this goal also links to multiple goals such as goal number 3, which is about good health and well-being. One thing worth mentioning is that the worst suffering countries do have plenty of brackish or untreated water in the form of rivers or water bodies accumulated from falling rain. And also, they do have abundant incident solar radiation according to the solar radiation map shown in figure 3. So, what are quantum dots? Quantum dots are defined as crystalline semiconductor nanoparticles that have different optical and electrical properties compared with bulk particles due to quantum confinement. An interesting feature of quantum dots is that they have a tunable bandgap, where bandgap is defined as the energy required to excite an electron from the valence band to the conduction band. This tunable bandgap property allows controlling the light being absorbed and emitted from the quantum dot system. Why in glass? For a few reasons. First, quantum dots may degrade and may be toxic, therefore dispersing them in a glass matrix provides an adequate host. Also, glass is relatively cheap to manufacture and has good chemical, mechanical, and optical properties. Therefore, it provides the opportunity for quantum dots to behave as radiation-absorbing hotspots. Please note that my project is part of a larger project, and the larger project has a main aim of designing a reasonably affordable and sustainable water treatment technology that uses the available incident solar radiation. However, my research is focusing on answering the following question, which is, can quantum dot glass be used as a material to heat up water to the boiling point through the absorption of solar radiation? As part of my experimental work, I have investigated the viability of the concept of the project, where I have used a commercial Pyrex glass vessel, filled it with a known amount of water, and heated it using a halogen lamps. And from the right-hand side graph, you can see that the results show that at a light energy intensity of 6.5 kilowatt hours per meter squared, the 2 liters of water reached a temperature of around 84 degrees Celsius with a stable surrounding temperature at around 30 degrees Celsius. One essential part of our project is revolving around the quantum dot selection to be doped in the glass matrix. And for this, we first investigate the materials that absorb in the available solar radiation spectrum, and we try to pick a material or a combination of materials that will absorb from all parts of the solar radiation spectrum. For example, this is the absorption spectrum of our telluride-based glass samples. They are doped with samarium oxide with cadmium sulfide, and samarium oxide with zinc sulfide quantum dots. As you can see, there are a few differences in the absorption behavior of the materials as the quantum dot materials and sizes are changed. However, the general output from this is that this kind of quantum dot glass systems does absorb in large parts of the infrared region and also some parts of the ultraviolet region. Finally, I would like to show you how we characterize different glass samples photothermally, where we use this experimental setup Basically, we hold up the glass samples and we put it in front of a known amount of radiation, and then we measure the temperature as it heats up and cools down. And what we can see is that because these samples have a slightly different absorbing properties, their heating rate and maximum temperature reached is a little bit different, whereas the cooling seems to be consistent with all samples regardless of their quantum dot structures. Thank you for listening.